So here we're going to talk about resonance in open air columns, but here's a little bit of review from force vibrations and mechanical resonance. Resonance occurs when the frequency of the forcing vibration is blank the natural frequency of the object. Those frequencies have to be equal. So the forcing vibration has to have a frequency that's equal to the natural frequency of the object, also known as the resonance frequency. So that's another, so it's the natural frequency or the resonant frequency. That's another term that we'll use to describe that frequency. So resonance in open air columns. We talked about vibrating strings in our last lesson, and those are vibrations you can see if you slow them down in a slow motion video, for example. And I suggested that you look at some of those on YouTube. But with air columns, you can't see the vibrations because they're invisible, but those vibrations still occur. So while stringed instruments obviously use vibrating strings, wind instruments use air columns, where we have resonance taking place in either open air columns or closed air columns. And we'll talk about the difference between those as well. Most of these instruments are open air columns, which means that they're open at both ends. There may be some that are closed, but I think those are pretty rare. A drum would be probably one example. So most of these instruments are a hollow tube, which is your air column, and it's open at both ends. So we call it an open air column. So because the end of the tube is uncovered and so then it's open, it means that the air at that end can vibrate freely. So it would be kind of like having a string that's not attached at one end, or at both ends in this case. So when it vibrates, you wouldn't get a node at that end. Instead, you'd get an antinode at the open end. So that's what we mean by an open end air column, or an open air column. It's open at both ends, so the air is free to vibrate at both ends. So the air inside the air column will resonate at certain frequencies, and only those frequencies, and a standing wave is produced. Now the standing wave wouldn't look like this, because this looks more like a string. Strings are attached at both ends, so here we have ends that can't move. With an open air column, we would have antinodes at either end, so it would look like this, because the air is able to vibrate back and forth at those open ends. So a closed end in an air column would be like the fixed end of a string. So you'd have a node, but as I said, the open end, at the open end you have an antinode because the air is free to vibrate. So then what would the first harmonic be like? Again, that's also called the fundamental frequency. So when the air column is vibrating or oscillating in the first harmonic, it's vibrating at the fundamental frequency. So for an open-end air column, let's have a look. It would look something like this. So again, notice that because the air column is open at both ends, it means the air can oscillate freely at both ends, and so we have antinodes like this, rather than having nodes like we saw with the guitar string. So how much of a wavelength is that? Well, a wavelength would be, remember that to measure a wavelength, we could measure it from antinode to the next antinode. So for a wave like this, if I draw part of a wave like this, then this distance from one crest to another is one wavelength, like so. So that's one wavelength from one crest to the next. So that's what we've shown down here at the bottom. And how many of those do we see? Well, if we look at the first harmonic, we see that we've gone half that distance. So we've gone from a crest to a trough. So we have half a wavelength shown here. So this is going to be half a wavelength. Half lambda. That's what we're showing there. So that means that the wavelength is equal to 2 times the length of the air column when we rearrange that. With higher harmonics, if we look at the second harmonic and the third harmonic, these are also sometimes called first and second overtones. So the second harmonic is the first overtone, and the third harmonic is the second overtone. If you're a musician, you may have heard that before. For an open air column, let's see what that. For the second harmonic, remember we still have to have an antinode at each end, like so. So if we were to draw the wave, it would look something like this. Keep in mind we're drawing these waves as transverse waves. We know that sound waves are not transverse waves, they're longitudinal waves, but those are really hard to draw. So we're drawing them as transverse waves just because they're easy for us to draw and to visualize. So, how many wavelengths do we have now inside the open air? Well, here in the second harmonic, from here to here, we have half a wavelength because we've gone from a crest to the next trough. If we go to the next crest, now we have 1 full wavelength. So the length of the air column in this for the second harmonic is equal to 1 full wavelength. How many do we have for the third? For the third harmonic, we've gone from, if we go from here to here, we have 1 complete wavelength, similar to what we just saw with the second harmonic. So there's 1 complete wavelength, like so, from one crest to the next crest. And then we've gone to the next trough. So now we've got the length in this case is equal to 1.5 wavelengths, like so. So what's the ratio of the frequency of the second harmonic to the frequency of the first harmonic? So now we're talking about frequencies. Well, as we go from the first harmonic to the second harmonic, we see that the wavelength will be half as great since we can fit more waves into the same length of column. We can fit twice as many wavelengths in. We've gone from half a wavelength to a full wavelength. And so if the wavelength has decreased like that, then so we've divided the wavelength by 2, then we must have multiplied the frequency by 2. So we get twice the frequency. So if we go from the first harmonic to the second harmonic, then the frequency of the sound doubles. Let's try an example. Determine the length of an open-ended air column required to produce a fundamental frequency of 480 Hz. So that's the first harmonic. So determine the length of an open air column required to produce a fundamental frequency of 480 Hz. We know that the speed of sound in this example is 340 meters per second, which is quite reasonable. So if we draw the diagram to show what the first harmonic would look like, again, as we saw earlier, we've got half a wavelength here. So the length of the air column must be equal to over 2. We'll write down our given values. So we have 480 Hz for the frequency. We've got the speed of the wave is 340 meters per second. Our wavelength at this point is unknown, and so is the length of the air column. We'll find the wavelength first. So using the universal wave equation, V equals F lambda, we'll rearrange that to get lambda equals V over F. And then we'll substitute the values in that we know. So the speed of the wave, 340 meters per second, divided by the frequency of the wave 480 hertz, and we get 0.708 meters, or 70.8 centimeters. Now we can find the length of the air column. Since the length of the air column has to be equal to half a wavelength, we can just substitute that in, and we get 35 centimeters, or 0.35 meters, for the length of the air column that will produce that frequency of sound. Alright, so now we're going to try an activity in which you build your own device with open air columns, and we'll see if we can play some music.